Welcome to another deep dive. Today, we're going to be looking at the world where machines are learning to decode human language,
Yeah, the fascinating realm of natural language processing.
NLP.
NLP. You sent us a syllabus from a course on AI for text analytics at National Taipei University. And something tells me you're particularly interested in one specific topic.
Oh, yeah. Transformers.
Transformers, exactly.
Super.
It seems like everywhere you turn these days, you hear about Transformers revolutionizing everything from chatbots to search engines.
Exactly. So let's get right to it. What are transformers?
Yeah.
And why are they such a big deal in the world of NLP?
Imagine trying to teach a computer to understand a sentence.
Okay.
It's not as simple as just recognizing individual words.
Right.
You need to grasp the context, the relationships between words, the nuances of grammar and syntax.
Nuances?
That's where transformers come in.
Okay.
They're a type of neural network architecture that's incredibly good at understanding the complexities of human language.
Okay, that sounds impressive, but how do they actually work? The syllabus mentions this groundbreaking paper, Attention is All You Need?
Yeah,
Is that where the magic begins?
absolutely. That 2017 paper introduced the world to transformers, and the field of NLP hasn't been the same since.
Attention is all you need. Sounds almost like a self-help mantra.
It does, doesn't it? But in the context of transformers, attention refers to a specific mechanism that allows the model to focus on the most relevant parts of a sentence when processing information. Think about how you read a text.
Yeah.
You don't give equal weight to every word.
Right.
Your brain naturally focuses on the key words and phrases that carry the most meaning.
Right.
Transformers do something similar.
So it's like having a mental spotlight highlighting the important bits.
Exactly. And this ability to selectively focus is what makes transformers so powerful. They can understand the relationships between words, even if those words are far apart in a sentence.
Okay, so we have this concept of attention that helps the model prioritize information. But before we get too deep into the technical details, can you give us a sense of the bigger picture? What are some of the key players in the transformer family tree, so to speak?
Well, since that 2017 paper, there's been an explosion of transformer-based models, each building on the original concept and pushing the boundaries of what's possible.
Okay.
You have BERT, GPT, XLNet, Roberta Paula. The list goes on. And of course, the one everyone's talking about these days, ChatGPT.
Ah, yes, ChatGPT. The
Yeah.
chatbot that seems to be everywhere. Is it fair to say that transformers are the driving force behind these large language models, LLMs, we keep hearing about?
Absolutely.
Okay.
LLMs like ChatGPT are trained on massive data sets of text and code. And they're able to generate incredibly human-like text, translate languages, write different kinds of creative content, and answer your questions in an informative way, all thanks to the power of transformers.
It's mind-boggling how far this technology has come in just a few years. So let's zoom in on one of these transformer models, BERT. You mentioned it earlier, and the syllabus seems to highlight it as a key player.
Right.
What makes BERT so special?
BERT, which stands for Bidirectional Encoder Representations from Transformers,
Okay.
was a real game changer when it came out in 2018. One of the key innovations of BERT is its bidirectionality.
Okay, break that down for me. What does it mean for a model to be bidirectional?
Think about how we read a sentence. We understand the meaning of a word not just by looking at the words that come before it, but also by considering the words that come after it. BERT can do the same thing. It processes text in both directions simultaneously, allowing it to grasp the context of a word much more effectively.
So it's like having eyes in the back of your head, but for language. That seems like a huge advantage over previous models that could only read text in one direction.
Exactly. This bidirectionality allows BERT to capture nuances and relationships between words that other models missed. And it's particularly powerful for tasks like sentiment analysis.
Ah, sentiment analysis. That's where a computer tries to figure out the emotional tone of a piece of text, right?
Right.
Like whether a customer review is positive or negative.
Right. Let's say you have a review that says, this movie was a total disaster.
Okay.
A model that only reads from left to right might get stuck on the word disaster and label it as negative, even though the overall sentiment is clearly ironic.
Right.
But BERT, with its bidirectional understanding, would be able to pick up on the sarcasm and correctly classify the review as positive.
That makes sense.
Okay.
Context is key, especially when it comes to humor and sarcasm. So BERT is the master of understanding context and relationships between words. What about the other side of the equation, generating text?
Well, that's where models like ChatGPT really shine.
Okay.
These are the large language models we talked about earlier, and they're incredibly good at producing coherent and even creative text.
So while BERT is like a meticulous reader, ChatGPT is the eloquent writer.
A great analogy. ChatGPT and other LLMs are trained on massive data sets of text and code, allowing them to learn patterns and generate text that's often indistinguishable from human-written text. They can write stories, poems, articles, even code, you name it.
But is bigger always better when it comes to these models? Is there a point where having more data and more parameters doesn't necessarily lead to better performance?
That's a very important question, and it gets to the heart of some of the challenges and limitations of LLMs.
Okay.
While these models are incredibly impressive, they're still essentially statistical machines.
Right.
They're very good at recognizing patterns and generating text that fits those patterns, but they don't truly understand language the way humans do.
So it's like a super-powered autocomplete, but not quite sentient.
A good way to think about it. And this lack of true understanding can lead to some interesting and sometimes problematic results.
Oh.
For example, LLMs can sometimes generate text that's biased or factually incorrect simply because those biases or inaccuracies were present in the data they were trained on.
That's a crucial point.
Yeah.
It reminds us that these models are tools, and like any tool, they can be used for good or for ill. It's up to us, the humans, to be aware of their limitations and use them responsibly.
Absolutely. Now, we've talked about BERT and ChatGPT as examples of specific transformer models, but to really understand how these models work, we need to take a closer look at the underlying architecture. The syllabus mentions this encoder-decoder framework.
Okay.
What's that all about?
Okay, I remember seeing that in the presentation. Encoder-decoder. Sounds a bit like a secret code.
It's more like a conversation, actually.
Okay.
Think of the encoder as the listener.
Okay.
Its job is to process the input text, break it down into its constituent parts, and create a representation of its meaning that the decoder can understand.
And the decoder is the
Think of that. The decoder takes the encoded information and uses it to generate an output.
Okay.
This output could be a translation into another language, a summary of the input text,
Right.
or even a response to a question.
So it's like a translator whispering into a diplomat's ear, and then the diplomat delivers a carefully crafted response.
I love that analogy. Now, to make this conversation truly meaningful, we need to talk about attention mechanisms, the secret sauce that makes transformers so effective at understanding and generating language.
Okay, this is where things get really interesting.
Yeah.
We've already touched on the concept of attention, but can you give us a more in-depth explanation of how it works within the transformer architecture?
Let's dive in. Imagine you're trying to understand a long, complex sentence. You're not going to give equal weight to every word right.
Right.
You're going to focus on the key words and phrases that carry the most meaning. Attention mechanisms allow transformers to do the same thing.
So like a mental highlighter emphasizing the most important parts of the text.
Precisely. And this selective focus is crucial for understanding the context and relationships between words, even if those words are far apart in the sentence. For example, in the sentence, the cat sat on the mat which was blue. The attention mechanism would link which to mat, helping the model understand that it's the mat that is blue, not the cat.
Ah, so it avoids those classic pronoun confusion mishaps. But how does the model actually determine which words are the most important? Is there some kind of ranking system?
There is. It involves a process of calculating weights for different connections between words. Words that are strongly related to each other based on the context of the sentence will get higher weights, indicating that they're more important for understanding the meaning.
So it's like a popularity contest for words with the most relevant ones getting the most attention.
I like that. And the more attention a word gets, the more it contributes to the final output of the model.
Okay, this is starting to make sense. So we have this concept of attention where the model selectively focuses on the most important words in a sentence. But the syllabus also mentions something called multi-headed attention.
Right.
Is that just a fancy way of saying the model pays attention in multiple ways?
It is. Imagine having multiple sets of eyes, each focusing on different aspects of a scene. Multi-headed attention is like that. It allows the model to look at the same sentence from multiple perspectives, capturing a richer understanding of the relationships between words.
So one head might be focusing on the grammatical relationships between words, while another focuses on the semantic meaning.
That's a great example. And by combining the insights from all these different heads, the model gets a more nuanced and comprehensive understanding of the text.
It's like having a team of experts analyzing the same sentence, each bringing their own expertise to the table.
Exactly. Now, all this processing happens across multiple layers in the transformer architecture.
Right.
Each layer builds upon the previous one, refining the model's understanding of the text. It's like a multi-stage rocket, with each stage propelling the model closer to accurate and insightful outputs.
Okay, we're starting to see how all these pieces fit together. But before we move on to the next stage of the journey, I have one more question. We've talked a lot about how transformers analyze relationships between words, but what about the order of those words? Doesn't that matter for understanding the meaning of a sentence?
It absolutely does, and that's where positional encoding comes in. Imagine reading a sentence where all the words are jumbled up. It wouldn't make much sense, right?
My brain hurts just thinking about it.
Right. So to avoid this confusion, transformers add special markers or vectors to each word, indicating its position in the sentence. It's like giving each word a numbered ticket so the model knows exactly where it stands in line.
So even though the model is looking at the sentence bidirectionally, considering all the relationships between words, it still knows that the cat sat on the mat isn't the same as Matt Cat the on Satsy.
Precisely. Positional encoding ensures that word order is taken into account even with all the complex processing going on.
This is fascinating stuff. Okay, we've explored the concept of attention, both single-headed and multi-headed, and we've seen how positional encoding helps the model keep track of word order. Is there anything else we need to know about the encoder side of things before we move on to the decoder?
Just one more key concept, residuals.
Residuals.
Think of them as safety nets within the transformer architecture.
Safety nets. That sounds intriguing. Tell me more.
As the data flows through the multiple layers of the transformer, there's a risk that some information might get lost or distorted along the way. The residuals are like shortcuts that allow the model to access the original input data at different stages of processing.
So it's like checking your work as you go along, making sure you haven't strayed too far from the original meaning.
A perfect analogy. These residuals help prevent the model from getting lost in translation, so to speak, ensuring that the final output remains faithful to the original input text.
I'm loving all these analogies.
Yeah.
Okay, we've explored the encoders in depth, and I feel like we've gained a solid understanding of how it works. Now let's shift gears and talk about the decoder.
Okay.
What happens on the other side of this linguistic conversation?
Let's dive into the world of the decoder.
Okay.
It's where the magic of text generation happens. Remember, the decoder's mission is to craft an output.
Right.
A translation, a summary, a response,
Okay.
based on what the encoder has understood.
Right.
It's like taking that diplomat's deep understanding and turning it into a compelling speech.
So how does it know what to say? Does it have its own set of attention mechanisms too?
It does. The decoder uses two types of attention.
Okay.
Self-attention helps it look back at the words it's already generated, making sure everything stays coherent and flows naturally.
Okay.
It's like the diplomat checking their notes to avoid repeating themselves.
Makes sense. You wouldn't want a speech full of tangents and contradictions.
Right.
But it also has stay on topic, right? That's where the encoder comes back in.
Exactly. The second type is encoder-decoder attention.
Okay.
This is where the decoder focuses on the most important parts of the encoded input, the stuff the encoder highlighted as key to the meaning.
Okay. So it's like the diplomat glancing back at the translator's notes, making sure they're hitting all the crucial points.
Yeah.
Double the attention for a truly accurate and meaningful response.
A great way to put it. But there's still a bridge to cross.
Okay.
The decoder is working with this abstract representation of meaning,
Right.
all these numbers and vectors.
Yeah, it's still speaking in code at this point, isn't it?
Yeah.
What's the decoding process?
That's where things get a bit more technical,
Okay.
but we can still break it down.
Okay.
The decoder uses what's called a linear layer,
Okay.
followed by a softmax layer.
Linear layer, softmax layer. Those are some pretty dense terms.
Yeah.
Can we unpack them without getting lost in the jargon?
Absolutely.
Mm.
Think of the linear layer as a massive dictionary.
Okay.
It takes those numerical representations, those codes for meaning,
Right.
and maps them back to actual words in our vocabulary.
Okay.
It's the translator finding the perfect word to express the diplomat's idea.
Okay, so it's going from abstract meaning to concrete words.
Right.
But there could be multiple words that fit right.
Right.
How does it choose the best one?
That's the softmax layer's job.
Okay.
It acts like a judge, evaluating all the possible words
Right.
and assigning each one a probability score.
Hmm.
Whichever word gets the highest score based on the context and everything that came before it, that's the word the decoder chooses.
So it's not just randomly picking words, it's carefully considering all the options and choosing the one that fits best, just like our diplomat choosing their words diplomatically.
Right, precisely. And this happens word by word,
Wow.
building up the output sentence, paragraph, or whatever the decoder is creating piece by piece.
Okay, I'm getting a much clearer picture of this whole encoder-decoder dance now.
Good.
It's a fascinating process.
Yeah.
But how do we know if the decoder is doing a good job? How do we measure how well it's understanding and generating language?
That's where the concept of a loss function comes in.
Loss function.
Think of it like a grading system for the model.
A grading system. I'm intrigued.
Yeah.
Does it get a letter grade, like in school?
Not quite a letter grade,
Wow.
but the idea is similar.
Okay.
The loss function compares the model's output
Right.
to the desired output, the correct answer, if you will.
Right.
The closer the model's output is to the desired output, the lower its loss.
So it's like aiming for a perfect score with each error adding points to the loss.
Exactly. And during the training process, the model uses this feedback from the loss function
Okay.
to adjust its parameters, its internal settings, if you will,
Right.
to get better and better over time.
So it's not just a one-time test.
Right.
It's a continuous learning process, always striving to improve its performance.
That's one of the things that makes these models so powerful.
Right.
They're constantly learning and adapting, getting better with experience.
It's almost like they're developing their own linguistic intuition over time.
That's a great way to put it. Now, before we move on, I want to take a step back and talk about one of the things that makes transformers so revolutionary, this idea of transfer learning.
Okay.
It's mentioned in the syllabus.
Yeah, you mentioned transfer learning briefly earlier.
Right.
But I'm still a bit fuzzy on what it actually means.
Imagine you've learned to ride a bike.
Okay.
You've mastered balance, coordination, steering.
Right.
Now, let's say you want to learn to ride a unicycle.
Okay.
You don't have to start from scratch, right?
Yeah. You can apply a lot of the skills you learned on the bike to the unicycle.
Exactly.
About transferring knowledge from one domain to another.
Exactly. Transfer learning is like that for transformers.
Okay.
Instead of training a model from scratch for each new task, you can take a model that's already been trained on a massive data set, like all of Wikipedia,
Yeah.
and fine-tune it for your specific task.
So it's like giving the model a head start.
Yes.
It already has a good understanding of language in general.
Yeah.
So it can learn new tasks much faster and with less data.
Precisely. And this is one of the reasons why transformers have been so successful. They can be adapted to a wide range of tasks with relatively little effort.
That's incredible. It seems like transfer learning is a major breakthrough in AI efficiency.
It is.
Are there any downsides or limitations to this approach?
Well, one potential issue is bias.
Okay.
If the model was pre-trained on data that contains biases, those biases can carry over to the new tasks.
Right.
It's something researchers are actively working on, trying to mitigate bias in these models.
That's an important point. It
Right.
reminds us that even though these models are incredibly sophisticated, they're still products of the data they're trained on.
Right.
We need to be mindful of the potential for bias and work towards creating models that are fair and equitable.
Absolutely. Now let's talk about one of the most powerful tools for working with transformers,
Okay.
the Hugging Face Transformers library.
Hugging Face.
You've sent us some Python code snippets using this library, and it looks like you're eager to dive in and get hands-on.
I am. The syllabus mentions Hugging Face as a key resource for this course.
Right.
And I've heard so much about it in the tech world. What makes it so special?
Hugging Face is like a playground for NLP enthusiasts.
Okay.
It's a platform that provides access to a vast collection of pre-trained transformer models ready to be fine-tuned for specific tasks. And it's incredibly user-friendly, even for beginners.
So instead of having to build a transformer model from scratch, I could just grab a pre-trained model from Hugging Face and adapt it to my needs.
That sounds amazing. What kind of tasks can I use these models for?
The possibilities are almost endless. You can use Hugging Face models for text classification, sentiment analysis, question answering, summarization, translation, you name it.
Wow.
And the library provides all the tools you need to fine-tune these models for your specific data set and get impressive results.
Wow, that's quite a toolkit. I'm already starting to see how Hugging Face can be a game changer for anyone working with NLP.
But I have to admit, even with all this talk about attention mechanisms and encoders and decoders, I still feel like I'm missing a visual.
Okay.
How do all these pieces actually fit together? How does data flow through the different layers of a transformer?
I knew you'd ask. Luckily, we have a secret weapon.
Okay, I'm all ears. What is it?
The Illustrated Transformer,
Ah.
a brilliant visual guide by Jay Alamar. It takes the complex architecture of transformers and breaks it down into clear, easy-to-understand diagrams.
Visual aids. I love it. So we're finally going to see what's going on under the hood.
The illustrated transformer shows us how data flows through the encoder and decoder, highlighting key steps like embedding words into vectors.
Embedding words into vectors. Now that sounds intriguing.
It is. Imagine plotting words on a graph,
Okay.
where words with similar meanings cluster together.
Right.
That's what word embeddings do.
Okay.
They turn words into numerical coordinates that capture their meaning and relationships.
So it's like giving each word a unique location on a map of meaning.
Precisely. And this numerical representation is what allows transformers to process language in such a powerful way.
Okay, this is blowing my mind. I can't wait to dive into the illustrated transformer and see all these concepts come to life visually.
I think you're going to love it. It's one of the best resources for understanding the inner workings of transformers.
But before we get lost in the visuals, let's take a moment to recap what we've learned so far.
Great idea. We've covered a lot of ground.
We started by exploring the concept of attention, the ability of transformer models to focus on the most relevant parts of a sentence. We saw how multi-headed attention allows them to analyze text from multiple perspectives, and how positional encoding keeps track of word order, even with bidirectional processing.
Right. Then we dove into the encoder-decoder framework, where the encoder acts as the listener breaking down the input text, and the decoder acts as the speaker generating an output based on the encoder's understanding.
And we learned about this fascinating concept of transfer learning, where models can be pre-trained on massive data sets and then fine-tuned for specific tasks, making them incredibly efficient and adaptable.
We also touched on some of the challenges and limitations of these models, such as the potential for bias, reminding us that we need to be thoughtful and responsible in how we develop and use these powerful tools.
And now we're about to embark on a visual journey into the heart of a transformer with the illustrated transformer, which will show us how data flows through the different layers and how words are transformed into these numerical representations called vectors.
Exactly. The illustrated transformer is a fantastic resource for visualizing the inner workings of these models. It takes these complex concepts and makes them accessible through clear and engaging diagrams.
I'm excited to dive in, but before we do, can you give us a quick preview of what we're going to see? What are some of the key takeaways from this visual guide?
Well, one of the things you'll see is how the input text is first broken down into individual words, and each word is then embedded into a vector.
All right, we talked about word embeddings earlier. It's like giving each word a unique location on a map of meaning based on its relationship to other words.
Exactly. And you'll see how these word vectors then flow through the different layers of the encoder, with each layer applying attention mechanisms and other transformations to extract meaning and relationships from the text.
So we'll get to see the attention mechanism in action, those mental spotlights highlighting the most relevant parts of the sentence.
You will. And you'll see how the output of the encoder, this rich representation of the input text, is then passed to the decoder.
And the decoder uses that information to generate an output, whether it's a translation, a summary, a response to a question, or even a creative piece of writing.
Precisely. And the illustrated transformer shows how the decoder uses its own set of attention mechanisms to ensure that the output is coherent, grammatically correct, and relevant to the input.
I can't wait to see all these pieces come together visually. I have a feeling this is going to be a real aha moment where everything finally clicks into place.
I think you're right. Visualizing these concepts can be incredibly helpful for understanding how transformers work.
So where can our listeners find the illustrated transformer? Is it part of the course syllabus?
It is. You'll find a link to the online version in the syllabus. It's freely available, and I highly recommend checking it out.
I'm adding it to my reading list right now.
Mm.
Okay, we've covered a lot of ground today. We've gone from the basics of natural language processing to the inner workings of transformers, exploring concepts like attention mechanisms, encoders, decoder frameworks, transfer learning, and even word embeddings. It's been an incredible journey.
It has, and we've only scratched the surface of this fascinating field. The world of NLP is constantly evolving with new models and techniques emerging all the time.
It's exciting to think about what the future holds for language AI. Who knows what amazing applications will be possible with these increasingly sophisticated models.
The possibilities are truly endless. But for now, I encourage you to dive into the resources we've discussed today, explore the world of transformers, and see what you discover.
And who knows, maybe someday you'll be the one developing the next groundbreaking language AI model. Until then, happy exploring.